Hello, this is Jack Jackson. We're going to be looking at piecewise defined functions today. And piecewise defined functions have different formulas that apply to different portions of their domain. So let's think of it this way. We've often thought of functions as like little factories. And an input or x walks in the door, and the factory then somehow transforms that input into some kind of output. So, that we think of it as a transformative process by turning an input into an output. So if we think of a factory model for a function, then for a piecewise defined function, there's a receptionist at the door. And when the x value walks in, or first coordinate or input walks in the door, the receptionist looks at that input and says, "Hey, what kind of input are you anyway? Oh, okay, you're in this category? Well, you go over here to assembly line A. Oh, you're a different kind of X next? Oh, you go to assembly line B or C or D." And so each of these assembly lines is like their own little factory, their own little function. It has its own little rules for turning and its own little process for turning an input into an output. Now, the overall result is you take inputs to outputs, but what happens to each input is a little bit different depending on what kind of input that you have. So let's start with an easy example. Here's one, f of x equals 15 for x is less than or equal to 10, and it's 1.5 for x is greater than 10. So, the receptionist looks at an input. Okay, they get an input of 5. Okay, the receptionist looks down at her rules and says, okay, is 5 less than or equal to 10, or is 5 greater than 10? Well, 5 is less than or equal to 10, so you go to assembly line A. Now, assembly line A is not very imaginative. They always turn everything into a 15, no matter what. So, what's the output? 15. Let's pick another x. X is 2. Well, again, 2 is less than 10. Goes to assembly line A, turns into 15. How about x is 10? Again, goes to assembly line A, and it is turned into 15. What about x is 11? Oh, no, wait a minute. Now, this time it goes to assembly line B. Well, assembly line B doesn't care what they get, but they're only going to get x is greater than 10. And what happens to it? Well, it's going to take that 11, which they got this time, and multiply by 1.5, which will give you 16.5, and so forth. So this graph and table will also be in two parts. In this particular example, the two parts, one kind of picks up where the other left off, so we end up with a continuous graph. But oftentimes we have breaks in the graph where we have breaks in the categories. So in this case, we should probably have arrow on the right end where it's going up forever and to the right, and on the left where it's going to the left forever. So notice that for the x is less than or equal to 10 in the table, I have some of those in red, and they are all turned into 15 for the output. For some x is greater than 10, you can see those in blue in the table, and they're multiplied by 1.5. Now notice that this blue part doesn't stop at 11, 16.5. There are values to the left of that are still in the blue part. For example, if I plug in, say, 10.5 for x, it is going to be going by that blue formula, so it's going to be still part of that blue line. Now, actually, it's not a whole line because it only goes forever in one direction. It's actually a half of a line or a ray. So here we have two half lines or two rays put together, and it just so happens that they have a common endpoint. So this blue one goes down to but does not include the point 1015, whereas the red one does include the point 1015 and goes to the left. So ultimately, you get a solid. Well, you get geometrically what this is an angle, right? You get two rays with a common endpoint. And so that's what the graph looks like. Okay, so let's see if you can try one. We'll give you one with 3 pieces. So try this one and make a graph. Now remember, your graph is going to be in 3 parts. Okay, And be sure to identify the boundary points of each part. And if a boundary point is not included, it'll be an open boundary point, and it'll be graphed with a little circle that's not shaded in. And if it is a closed boundary point, if that boundary point is part of the graph, it'll be actually in the table then, and it will be a solid dot filled in circle. Okay? So see if you can work this out. Come back when you've made your attempt at that. Press pause now. Well, here's the solution. For x is less than -2, we use the y's get turned into 3. For x is between -2 and 4, we use the formula y equals 2x. For x is greater than or equal to 4, we use the formula -3x plus 16. Okay. Now I've made these 3 different colors, and I'm going to make it easier to see the 3 parts of the table, the 3 parts of the graph. But ultimately, this is just one function. Okay, so even though these are 3 assembly lines within the one factory, it's ultimately one big factory. And so really, probably these ought to be all the same color because it's all the same function. Okay, but I think the color helps us here. Okay, so I made a table with integer values going from -4 to 7 for inputs. And I've colored the ones with the blue color there when they fall in assembly line 1, and then that for those x's, -3, -4, any x's less than -2, we're going to use the formula y equals 3. And so the output is just 3. Pretty simple. When we go from -2 to 4, including -2 but not including 4, so the integer values, that would be -2, -1, 0, 1, 2, and 3, but not 4. So those are the ones that are red in the table, and that uses the formula 2 times x for the y. And so you can see that -2 doubled is -4, -1 times 2 is -2, 0 times 2 is 0, and so forth. And so we get those values. Now when we actually get to 4, it actually jumps over to the purple piece, the third part of our function, and the y is determined by the formula y equals -3x plus 16. So we use that. -3 times 4 is -12 plus 16 is 4. -3 times 5 is -15 plus 16 is 1, and so forth. And we see the purple part, they're going down by 3 each time, because we know it's a linear equation. We know all about those. And the red part is going up by 2 each time we go up 1 in x. Whereas the blue part is just staying the same all the time. So each of these pieces, being linear functions, are going to be linear pieces. The first piece is actually a constant function, so it is a line, but it's a horizontal line. And the next piece is going to be a part of a line. So we had part of a horizontal line to start with. We have part of a line with slope 2, positive slope line there, for the red piece. And the purple piece is a line, part of a line, with the slope of -3. Now let's look at the last piece first, the purple piece. How far to the right does it go? Well, x's go on forever to the right, and we still use that formula. So you can see an arrow down in the bottom right part here of the, down in here, bottom right part of the graph. And so that indicates that that part of the graph goes on forever to the right, and in this case down. Now how far to the left does it go? Well, it goes down to and including the point when x is 4, and we've already worked that out. That's 4, 4. And so 4, 4 right here is a closed boundary point. Now let's look at the far left. Okay, how far does it go to the left? Well, again, forever to the left, and so that's why we have an arrow on this piece on the left. So that says it's going to the left forever, and it stays the same out there at 3. So we have a horizontal line coming in, or part of a horizontal line. Now how far to the right does it go? A common mistake students make is a couple mistakes. They think they need to connect up all 3 pieces. These 3 pieces are not connected. There's a break where we have a break in the definitions. So there's no guarantee that these pieces will meet up. Now the one we looked at the first example, it just so happened that the open dot at the end of this blue one was right on top of the closed dot at the end of the red one, and they did meet up, so we got a continuous function. But that's going to be a special case. So here is a more typical case where the pieces perhaps might not meet. In this case, they don't meet. There's a break, what we call that a discontinuity, a break in the graph. Okay, so let's look at this a little bit further. So at this first piece, I've got it at negative 3, 3. Now when you get to negative 2, actually the graph jumps down to negative 2, 4. We move to the red piece. But what about stuff that's close to negative 2, but a little bit to the left? Now a common mistake for students is to stop right here at this last one, blue one we see in the table, negative 3, 3. But in fact it goes to the right some more, because you can put in, say, negative 2.5, and you also get 3. And negative 2.1, and you get 3 for the output. And negative 2.1, comma 3. Negative 2.01, comma 3. Negative 2.00000000001, comma 3. So what happens? This keeps going to the right, up to, but never quite hitting that boundary point. And what is that boundary point? Well, that boundary point is negative 2, 3. How can we find that? We can find that by pretending that negative 2 does work in that first part. Okay, and if we were to give a negative 2 to the guys in the assembly line there, they would turn it into a 3. Of course, the receptionist never actually sends that point, that input to those folks, but you know, that goes right up to there. And so negative 2, 3 is an open boundary point. Now we actually get a solid boundary point here at negative 2, 4. Now why is one solid and one open? Well, the one that was open here at negative 2, 3 is because we have a less than here. There's no equal to part. The equal to part's on the red, and that's the part that's going to have the solid boundary point. Just like the equal to part was on the purple here at 4 and on the last piece, and so that's why the purple part has a solid boundary point. Now, again, the next part you want to be careful about is the points between 3 and 4. So x is between 3 and 4. This little part of the graph right in here, if you can see my little cursor moving around, this part of the graph is still on the red. Between 3 and 4 here. Okay. And I don't have that graph right, or it doesn't match everything else. So I'll go back and fix that here in just a second, because this point is not, that's supposed to be 4, 4, not, and that's supposed to be 4, 8, not 4, 10. Okay, so let me actually see if I can fix that. I think, well, I'll fix it. Yeah, I'll fix it now. I did this one in Geometry Sketchpad. So give me just a second, and I'll show you how I did this. And I'll show you another way you can do this if you don't have Sketchpad, but it doesn't. Okay, so we had 3 pieces. This one was at 3, and it went forever there, this way. And it goes up to, where again? Let's go back. Goes up to negative 2, but doesn't include negative 2. Okay, so negative 2, and that's 3. Alright, that's our blue piece. Our red piece went down to, should go from negative 2, negative 4 to 4, 8. Negative 2, negative 4, and negative 2, negative 4 is there. Negative 2, 3 is there. negative 2, negative 2, negative 4, and then 4, there we go, there's 4, 8, there we go. So this should be 4, 8 for the open boundary point. And this one needs to go at 3. There we go. That looks good. And this one is negative 2, negative 4. And that one was closed. And this one should have been at 4, 2. Where was it? 4, 4. And it's going with a slope of negative 3. So that should go through 4, 4. And when we go the right one, we should go down 3. There we go. And this is our boundary point, is 4, 4. Okay, now we got the graph right. Take a look at that. It's 3 all the way up to, but not including this point at negative 2, 3. At negative 2, it actually jumps down here to negative 2, negative 4. Then this has a slope of 2, so right one and up 2. And it goes up to, but not including the boundary point at 4, 8. When it actually gets to 4, it jumps down here to 4, 4. And then it goes right one down 3 with the slope there, with a line that way. Okay, so let's take that, get that in our spreadsheet, get that in our PowerPoint, and replace that graph because it had a little bit of a problem with it. Okay, so there we go. Now the graph looks right. Okay? So pay attention to the boundary points. The boundary points are important. So you need to go ahead and plug in this negative 2 in this formula and get that point negative 2, 3. But since it's not an or equal to here, it's not actually in the table. It shows up on the graph as an open circle, open boundary point. You do put in the negative 2 in the formula here and get negative 4. Since there is an equal to here, that negative 2, negative 4 is in the table and it's a solid dot on the graph. You do plug in 4 in this and get 2, 8. 2, 8, since this is not a equal to, 4, 8. 4, 8 is not in the table, but 4, 8 is an open boundary point on the graph. You do plug in 4 into this formula here and get 4, 4. 4, 4 is a point in the graph, and it is a point in the table because of the or equal to here. Okay, let you try another one. Okay, so here's another one. This one's going to have 4 pieces. So make out a table here that's going to be enough table that you can tell what's going on in each of the 4 pieces, and graph these. The pieces, they're not all straight lines this time, but they're all something that we've studied. And then get a table, and then once you got the table, make your graph. Pay attention to whether you have open dots or closed dots on the boundary points. Okay, so go ahead and do this one now. Press pause. Okay, so hopefully we're in business here. So here I made integer values of inputs going from negative 6 to 13. You don't have to pick integers here, but we do have to pick enough of each piece that we get an idea of what's going on. And then we also have to figure out those boundary points even if they're not really in the table. So the first piece, our x is less than negative 2, so for those integer values, that's from negative 6 to negative 3 for the ones I have here. Really from negative infinity all the way up to negative 2. Okay? And so those, it's the formula x plus 9. So negative 6 plus 9 is 3, negative 5 plus 9 is 4, and so forth. And of course you see that the y values are going up by 1 because it's just a linear equation with slope 1. If we were to extend this out, we know that it would go through a y-intercept of 0, 9. And you could also think of that as factored form, so we know it has an x-intercept of negative 9, 0. Negative 9, 0 actually is on the graph. 0, 9 is not on the graph because it stops at the boundary point negative 2, 7. So notice I plug in negative 2 there. I say negative 2 plus 9 is 7. So negative 2, 7 is the boundary point of that piece. Is it included or not? Well, remember that the round parentheses here says it's not included. And so negative 2, 7 is not going to be in your table, and it's not going to be a point that's actually included on the graph, but it's a boundary point on the graph. So it shows up as an open circle dot, an open dot. Now for the next piece between negative 2 and 3 inclusive, that gives us these green values here in the table. We're just using the power function y equals x squared. We've done this one many times by now. And you know what that's going to look like. And of course we get part of this power function here. It stops at those endpoints of negative 2, 4 and 3, 9. And since this is the bracket on both ends, those are both solid boundary points. The next line segment piece, horizontal y equals 4, has open boundaries at both ends. So the part of the table over here that is in red corresponds to that, and of course all the outputs are 4, and we can graph all those points. We see that they're in a horizontal line. We knew that ahead of time. Y equals 4 we know is a horizontal line. But of course it's only part of that horizontal line going from boundary point to boundary point. The boundary point would be 3, 4 and then 10, 4. Those are both open boundary points, but we have solid dots in between them, including things like 3.1, 4 and 9.9, 4. But when we actually get to 10, then we use this formula here. Notice that's a linear equation with slope negative 2 thirds, and it goes through the point, if it's in the piece of the domain here, it goes through the point 10, 3. That's a point slope formula for a line. And of course 10 is exactly the boundary, so 10, 3 really is the boundary point there. We can see that, plug in 10 for x, and this is 0, plus 3 is 3. And this has slope negative 2 thirds, so it only applies by going to the right because 10 is the left boundary of this thing. But if we go to the right one, we go down 2 thirds, so that's 2 and 1 third, or 2.3 repeated. And then the next one is add up another, go down another 2 thirds, that's 1 and 2 thirds, or 1.6 repeating. Go down another 2 thirds, we're at 1. So for example, you get the point 13, 1. So you go to the right one, down 2 thirds, right one, down 2 thirds, right one, down 2 thirds. Or you could think of going right 3 and down 2, and that gives you the point here at 13, 1. And of course connect those up, and we get this half of a line array, and it does have a solid endpoint. Now these kinds of functions show up a lot in application problems, and there are certain kinds of things that work. So I'm going to give you an example of an application problem and see if you can take this real-world scenario, make up an appropriate formula for this. I'll give you a hint. It is piecewise defined. Okay, and figure out what the appropriate domain is in the context of the problem. Draw a graph of the function in a window that makes sense, and then make a table showing how this goes up in $500 increments. So this is a salesperson who earns a monthly base salary of $2,000 plus a commission of 5% of all sales over $1,000. They don't get any commission on the first $1,000, but any sales that they make over $1,000, they get 5% of the additional amount, not on the original $1,000. So they only get so if they sell $1,200, they get their $2,000. Plus they get 5% of the $200 that's over $1,000. Okay, so with that set up, go ahead and see if you can work this out. Press pause now. Well, notice that if S is our sales, P is our pay, and they're both in good old US dollars there, and notice the domain for this is the X values, or in this case the S values, the amount of sales. Well, you can't sell a negative amount of items. You could sell 0. there's no really upper limit to how much you could sell, although there might be some practical value beyond which they're not likely to sell it. So the domain here is from 0 to infinity, including 0. So, of course, when I set my window, I'm definitely not going to have any negatives for my my pay either. Okay, because they're guaranteed at least 2,000. They're not going to take away pay if they sell less. So this is definitely just a first quadrant graph. And notice the piece that's in red on the graph there is the piece of sales up to and including $1,000 of sales. Their salary is they just don't get a commission, so they just get their straight salary of $2,000. And so that's straight across horizontal. And in our table, I didn't color it red in the table because this is just one function, but you do see it there as the first part of this table with all the 2,000s here. Okay, now what happens if they get above $1,000? Then they get the 2,000 salary, base salary anyway. So you get that, plus you get your commission. What's your commission? Their commission. It's 5%, which is 0.05, of, which is times, the amount that's over 1,000 in sales. So that's S minus 1,000. Of course, at 1,000, that formula works out to be 2,000. So the boundary point there would be an open dot, but it actually is right on top of the closed dot on the other one. So this is a continuous function. So we don't get a big jump up or down there. Once we hit 1,000, it starts to go on up. Still in a nice connected manner, but now the salary starts to go up with a constant slope of 0.05, constant rate of change. That's linear, and so we see a horizontal piece followed by a linear piece with slope 0.05. And of course 5%, I'm going up in increments of 500. 5% of 500 is $25. So this is going to be going up in $25 increments on the table over here. If I were going up in $1 increments on the sales, then we would be going up in 5-cent increments on the pay. Okay, and so now you can see that in the table and in the graph. So there's an example of a real-world function. A real-world application. There are lots of them like this where the rules change at a certain point. You know, there's a salary up to a certain point, and then the commission starts kicking in. Now, if the commission kicked in from the beginning, you know, $2,000 plus a commission on all sales, then that would have been different. Okay, it would have been it would have been 2,000 plus 0.05 times S, and that would have been it, and it would have been just a line starting at 2,000 and going up and to the right with a slope of 0.05. But this part, by breaking it in pieces like this, of saying they only get this commission on the sales that go over 1,000, but they get their base salary no matter what, this makes it piecewise defined. Lots of things can work like this. You can say charges that they charge you for. Well, you get so much flat rate, and let's say you're renting a car, you get a flat rate. And then if you that'll include so many miles. Well, if you go over those miles, then it's so much per mile. That's going to be very similar to this setup here. So what should you be able to do now? You should be able to, if I give you a formula for a piecewise defined function, you should be able to make a table and graph. Special attention should be paid to those endpoints. And if I give you a real-world description that involves piecewise defined functions, you should be able to come up with a formula and a table and a graph and use them to solve some application problems. So this gives us a new way of combining existing functions in pieces. And so this is a new way to get new relations from old relations.